Okay. Yeah. So I don't know. Well, I might want to share my board, so that's probably. Okay, so this lecture is just going to be about vision transformers. I think so. One thing I think someone on STEM was wondering a bit um about transformers, just sort of like clearing up some of the specifics and like having a bit of a more concrete example, I guess. So the idea, like the highest level, is you have some set of tokens, like you have a sentence, right? Like that. Then you want to, the objective would be the autoregressive objective, for example. So that would mean given the cat, you want to figure out what the next token would be. So what would happen is you'd encode each of these words into embedding vectors, and then input that into the large transformer, and the transformer would output some set of embedding vectors. And then usually you'd have also like a CLS token, right? So based on the output representation of the CLS token, you'd then use that to make the classification of what token would go next after these first two tokens, right? So the way the attention mechanism works, right? So this transformer model has some number of blocks, transformer blocks, and each transformer block consists of first the attention mechanism. Let me just go like first the attention mechanism, and then the MLPs, that's the multi-layer perceptron. So, and then you have this input. Your each embedding goes through this, and then you also have a residual after each block, after each like submodule, right? So this then gets added to the output of this, and then this also gets added to the output of this. Right. So the attention mechanism itself is you have like some black box function that converts each of these embeddings to KQV, right? So that's key query value. So that's works pretty like intuitively as you'd imagine with like a database lookup, right? So each embedding K, you compare it to all of, or each embedding Q, take the query of each embedding, and you compare it to all of the key values of all of the other embeddings, right? And then you try to find the most relevant keys out of all of the tokens. So it could be itself, right? Because this also has a key embedding, right? And then you find the most relevant ones, and you take that value, and then that becomes the new representation, right? But of course, like this is all, this is soft attention. So instead of like a hard lookup, instead of just taking and copying the resulting value, you do dot products between all of the other embeddings. And then that way you have a probability distribution over which embeddings will be the most probable, and then you can take a weighted average. So then you have like the expected most probable like value out of each embedding, and that becomes the resulting. And then the multi-layer perceptron just applies the same linear layers over each of the resulting embedding vectors. So that just adds a bit more representation of power to the transformer. So for VIT specifically, we essentially just want to apply this architecture from text where it was originally used and originally very successful in, and we want to apply it to images, right? So this is like hypothetically a very, very intuitive motivation for why we want this architecture. Right, it works well for one domain, we want to use it for another domain. So transformers also have some really nice properties that would work really well for CV. So this includes scalability, right? They're really computationally efficient, as we talked about last time, right? They work really, really well with GPUs and TPUs, which is great. And also global receptive fields, which is something that we'll talk about a bit after. So yeah, I just went over transformer architecture a bit. Main thing though is that the way we pre-process this text, right? So we start with just a string, and then we want to tokenize this. So one way we can tokenize this is just by taking each word, right? So D becomes a token and cat becomes a token. And then we have some vocabulary that we can then, where we map every single word that's within our vocabulary to some like index value, right? So our vocabulary might be like the, that, I don't know, a, some set of values, right? This is going to be like a finite set of possible tokens that we can have, right? So the what might be 0, cat might be 1, and then our when we go through our tokenization process, the would have 0 and cat would have 1, right? And then to convert this to our embedding vector, we then have to look it up in some dictionary, right? So we'd also have this other embedding table where 0 corresponds to some dense vector and 1 also corresponds to some dense vector, right? So that's how we convert our tokens to our then like input embedding representation. So how do we then transfer this architecture to vision? How do we transfer this to images? So the one way is like to start off by thinking about what is like the simplest way to do this, like the dumbest way to do this. So one way would be just to flatten an image. So we usually have like some like 16 by 16 image, right? We flatten that into a that'll be 256 length vector, right? 16 times 16, where each item in that vector would be a pixel value, right? But the issue with that is we can't just input that vector into this transformer because color values are continuous, right? We can't really look them up in a table because then you'd have to have like an infinite length table. It's not really possible, right? So we have to find some way around this. Well, one way is to just pretend they're discrete, right? So like in practice, if images are stored in a computer, they're not going to have like infinite precision, right? They're going to be quantized to some amount, and you're going to have a limited set of bits to store each color value, right? So in that sense, you kind of have a discrete set of tokens, right? So each pixel is represented with 256 values per color dimension, right? But that means that you have this huge vocab size of 16 million, right? So you have like might have your like image that's like 256 long, and then each token, so each pixel value is a token, right? That's our assumption. Each pixel value is a token, and then each token has 256 times 256 times 256 possible values, because that's the number of color values there are in our representation. So that's too much because we just can't store like an embedding dimension of like 16 million. So one way around this is to just like use less colors, I guess. Instead of having a 24-bit representation, you have a 9-bit representation and 8 possible values per color channel. So RGB, and you have 8 possible R values, possible G values, right? This means you have a vocab size of 512. That's a lot more reasonable. That's definitely doable, right? So like each color value in this representation, this 8-bit or 9-bit representation, you look that up in your embedding table to get instead of mapping each like word to an embedding vector, you map each possible color to an embedding vector, and then you input it. So another problem is time complexity. So recall that transformers are n squared with respect to input length, and then also input length is n squared with respect to the length of each side of the image, right? So if you have a tiny like 256 by 256 image, that's like an input length of 65,000, right? That's way too much. For perspective, the maximum input length of BERT, which is another like transformer based, was a language model, but its max length is only 512, right? I think the max I've seen is like 2,000. So 65,000 is way too much. One way around this is just to use smaller images. Just like make it 64 by 64 instead of 256 by 256, right? And then the way it's trained like pretty similar to how language models are trained, which means it uses the self-supervised objective of given the first t-1 tokens, predict the tth token, right? So given the first t-1 pixel values, you predict the t pixel value. And that way, hopefully, you'd build good image representations. Which is sure, let's check the time. So the good thing about this is that you have really, really good image representations. So one way we can measure this is through semi-supervised classification, right? So the task specifically is classification, but with a limited set of labeled samples. So remember, our model, it's pre-trained on unlabeled samples, just like random images you can scrape off the internet. But now, given that pre-trained model, we want to do this task where we classify on a very small set of labeled samples. And the way we do this is we just pass all of our images through our model, and we take this output representation, right? We can just like take this output representation and like pull it or something. And then we use those as input into our linear classifier, and then we only train that linear classifier to do classification on those labels. And the only input features it gets are the output of the image GBT representation of the transformer output representation. So because we only have this limited set of samples, limited set of label samples, we can't train this transformer. It's just too large, right? We can only train this tiny linear classifier that only uses the output image representations in order to do classification, right? So in order for this linear classifier to do well, the output representations of the transformers need to be good enough that this like tiny weak classifier can classify images, right? That the image the output embeddings already have to be like linearly separable with respect to different objects, right? It already has to encode what's inside images, because this linear classifier needs to be able to use that representation in order to do classification, right? So the result is really good, right? It gets, you know, some really competitive results and without using labels, right? So it's able to get like 96% accuracy just with a very like limited set of image net labels, right? So another way you can sort of look at this is with image generation. So recall that the way we train this is autoregressive, right? Given the first t-1 pixels, we predict the teeth pixel. So what we can do is we just run that over and over again on this input like masked like elephant with butterfly ears, and then it's able to generate this elephant with butterfly ears while like with the understanding that like this is a weird elephant that has butterfly ears, and like this image probably doesn't appear much in the training set, right? But it's still able to sort of infer based on context what's inside the image and make these really good generations. So this also applies for like droplets. It can sort of do this like pseudo like physics simulation, I guess, and these CAD drawings too. So yeah, I think this is what sort of caught people's attention with this model and transformers applied to images. So the bad is that it takes a ton of compute, right? So they trained a 6.8 billion parameter transformer, and it was trained for 2,500 V100 days. So V100 is like a type of GPU, and essentially they used a ton of compute. And the transformer is only able to work on images with 64 by 64 resolution images, right? So that's pretty bad. So what's the point of this? So the point is mostly as a proof of concept, right? So this paradigm of transformers and massive self-supervised pre-training will apply to a completely new domain. So we use this paradigm of like transformers and a ton of pre-training data, unlabeled pre-training data, with text, and that worked really well. But now we want to apply it to like images, right? So we see that it does work, right? But we do need like a faster way to do it. Like this isn't going to work for any downstream applications. Yes.
The self-supervised function. What's the sort of loss function?
So you wouldn't actually train the transformer. You'd only train the linear layer on top, right? And then you can just do like a normal. I think they do like logistic regression. So you can just do like your normal like cross entropy objective in order to train your linear model. Except the model, instead of taking as input the images, it takes as input the output representations. So yeah.
But if you don't, do you have labels?
Yeah. So you have a very small set of labels. Yeah. So there are ways to make transformers more efficient, like architecture-wise, but recall that like a major appeal of using transformers is they scale really well relative to the amount of compute you have, right? So because the architecture is so simple, and because they're essentially just like huge matrix multiplies, they work really well with GPUs and TPUs. So we're able to scale them really well with the sort of hardware that we have. So yeah, that sort of justifies why we might want to keep the architecture more simple, even if they're like n squared with respect to input length, right? So a maybe more practical solution is from this paper. It's called an image. Can't speak today. An image is worth 16 by 16 words. So rather than quantizing pixels, we sort of downscale images by first splitting them into patches and then projecting them into our input embeddings directly. So remember last time with ImageGPT, we sort of we pretended that our pixels were tokens, and then we looked them up in a table, and then we use that table to get our input embedding results, right? But now, what if we just take our image, we split it into patches, and then for each of these patches, we do something like the KQV like projection. We just pass it through some linear layer, and we take that linear layer output to use as our input embeddings. So we just take that image directly, we process it a bit, and then we use that representation as the representation of that of that part of the image, right? So our tokens are essentially the patches, and the patches, instead of looking them up in a dictionary, we just use a model, a tiny model, to learn what the input representations would be. And then we also do the standard stuff of adding like position embeddings and like the CLS token in order on top of our transformer. Yeah. And then let's see. So some miscellaneous stuff for this architecture. So one thing is because pre-training like takes so much time, we go through so much data. We tend to want to pre-train at a lower resolution first and then fine-tune at higher resolution. We can also get patch representations using convolutional neural networks. So it's more of like a hybrid approach, I guess. So remember this linear projection just passes the patches through a linear layer. Instead, we can use a convolutional layer. That also works. The task that they do the benchmarks on is your standard like Imagenet classification. So so that's just image classification. Yeah, so the way they train this is they first do pre-training on like a massive data set. So the thing about this isn't self-supervised the way they do pre-training, right? They have like this weird Google has like this huge like closed source like 3 billion sized like image classification data set where there's like a ton of images, but the labels are also like really noisy because some of them are like automatically labeled, some of them are like hand labeled. So this is a bit different from before in that we're pre-training with a supervised data set. And then after we have our pre-trained model, we can then fine-tune it on the actual data set. So this gets really, really good results. It was state of the art for Imagenet, I think, or barely, but yeah. But the main thing is that relative to the previous state of the art, so this is the convolutional neural network. Relative to the previous state of the art, it is way more efficient. So this tells us how much compute it uses, and it uses like 1/5 of the compute of the previous state of the art. So the claim of this being a more efficient architecture is yeah, true. So sort of a quick aside on this term like inductive biases that we'll probably be using a lot. They're essentially like assumptions that you make by choosing some model, right? So if you choose, for example, like a linear model, then you're assuming that your data is linear, right? If your data is not linear, then your linear model is not going to work really well, right? So the claim, right, why vision transformers are maybe like better in the most like general sense of the word are better is because they're more general in the sense that they have less inductive biases, right? So the reason why a lot of people are really hyped about vision transformers is because one reason is because they have less inductive biases. So so specifically what they are for example, you have I'll just go over, I'll like compare and contrast the inductive biases that you have for CNNs versus for vision transformers. So CNNs on the left, you have the big two big ones are locality and two-dimensional neighborhood structure. So locality means that sort of image features that are closer tend to be like more biased toward you. Like the model tends to be more biased towards image features that are close together. So for example, if you have if you recall like the sort of sliding window architecture of your CNN, the only way in a single CNN layer, the only way that two pixels can sort of interact with each other are if they're within the limited kernel size, right? Because let's see. Surface. So you have your image, and then your CNN. What your CNN does is you have some like set of weights. These get applied in this like a sliding window fashion. So that you do the dot product between this and this, and this and this, this and this, right? So the only way that two pixels are going to interact is if they're within this range, right? So if you have two pixels here and here, then those get to interact, right? But if you have a pixel here and here, then those are way too far away, right? The output representation are still going to be on the opposite corners, right? Because it's limited by this tiny kernel size, which is going to be like 5 by 5, like 3 by 3 or something. And obviously, like two-dimensional neighborhood structure, if you're doing like a kernel with like 2D matrices, that's what you're going to have. You're going to assume that your input is also like 2D, right? Another thing is translational equivariance. So the thing here is like we apply the same weight matrix to each part of our image, right? So if we have an image feature over here, and an image feature over here, they're going to be treated the same way by this weights, right? Because we're just applying it in the same way here and here. So yeah, that's another big assumption that's made. So whereas with vision transformer, oh sorry.
So if you contrast the kernel method, so let's say those two pixels of those features far away, back.
Oh yeah, sure. Yeah, so remember like well this will all be like flattened out, but for a vision transformer, this will attend to everything, right? So this will project this out to like K, Q, V, and then each pixel will also have like a K, Q, V. This will also have like a K, Q, V. And then this query will attend to this pixel, this pixel, this pixel, right? Then also attend all the way over here to this pixel, regardless of how far away. Like each pixel will always attend to every other pixel. Or sorry, each token will always attend to every other token.
So the patching is it's a computational using the computations.
Yeah, essentially, yeah.
Second question is the translation, because you have different kernels. You end up with like different weights for each. So you can use like basically functions.
Yeah, so you do have different like functions for different features, but each of those functions get applied in the same way for each part of the image, right? So in like the translational equivariance appears if you share the same weight across positions. So yeah, whereas if you have a vision transformer, sort of each position, essentially each position is a unique token, and each unique token has its own representation for key query value. So then each representation also depends on the token. Also, you have like your positional embeddings as well, which also affect your resulting representations. Yeah, so that was CNNs, and then you also have the inductive biases for VITs. The only ones that you have are sort of image patches. So like image patch, if you're splitting your image into patches, and you're assuming that's going to be like a 2D image, right? And then also like positional embedding. So this is like, don't worry too much about this, but position embedding interpolation during fine tuning. So what that is remember that with this architecture, you want to pre-train at a smaller resolution and fine tune at a higher resolution. But the way that the positional embeddings are trained, right? They're trained as like an embedding vector, right? So you're gonna have like this limited set of positional embeddings that you're used to using for your model during pre-training. But when you actually fine tune at a higher resolution, then you need more positional embeddings. But so how do you like transfer your old positional embeddings to this like new set of positional embeddings? You're gonna need to interpolate between positional embeddings. But don't worry too much about this. Essentially, like the only inductive biases occur sort of at the input of your model, like when you're like sort of pre-processing. So it's much more limited than that of CNNs, essentially. So what this sort of means for this architecture is that VITs perform a lot worse when there is not as much data, and they perform better when there's a lot of data. So if you look at this graph, right? So the x-axis is the number of pre-training samples. The y-axis is the sort of accuracy. So the gray is CNNs. These are just ResNets, and then the blue, green, other stuff is VITs. So in the beginning, when there's not much data, ResNets perform better. At the end, when there's a lot of data, ResNets perform worse. Yeah. So sort of why is this trade-off happening with VITs? And then sort of how does this connect to inductive biases? So the sort of intuition is if we don't inherently bias the model towards any particular like mode of data, if we don't bias it towards images inherently, then it has to learn those representations from the data, right? So whereas with CNNs, a lot of these biases, they're already hand engineered, right? So if we sort of assume that like humans are dumb and like machine learning is smart, then if you have the machine learn its own representation, if you have the machine learn its own like way of processing images, then that might be better than if you have like humans try to engineer it themselves, right? So we can see some evidence for this with the types of representations that are learned by the model. So, for example, you have the position embeddings. So position embeddings, they're just like learned. They're initialized randomly. But even then, they still you can see that they still sort of encode position on the 2D plane, right? Because even if we flatten everything and input it into the model, it still encodes things like with like 2 axes, right? Another thing is like if we look at the intention map. So another thing transformers are great at is, or they're kind of okay at this, which is that attention lets us sort of see what the model is like looking at, makes it slightly more interpretable in some ways. So we can look at the attention representations and see that when you input an image, it tends to sort of look at the object in the image and ignores the background, right? And we can see us, not too sure where this is from, but you can see some of the representations that it has are sort of encoding like lines and textures and stuff, which are nice. If you might sort of like recall sort of similar ones that are learned by CNNs, which is pretty cool. So yeah, the sort of takeaway from this is that transformers are able to learn these biases, learn how to better represent images if we give them a lot of data, right? And it's able to learn these better representations because we don't bias it from the beginning, right? Whereas CNNs, if we bias it to process images in some way from the beginning, then it's not able to learn these better representations, right? So I mentioned this earlier at the beginning, which is another advantage. Vision transformers also have a global receptive field. So actually, yeah, we kind of touched this, which is if you have sort of something here and something here, if we want these two things to interact, we can't do that in like one or two convolutional layers, because after one or two because this kernel size limits us to only process things within this tiny area, right? So we're gonna need to wait until like the very end in order to have these two tokens relate to each other or interact with each other. Whereas with vision transformers, everything can attend to everything from the beginning, right? All tokens explicitly sort of like interact with every other token. So from the beginning, this token can, if it thinks this other representation is important, then it can just look at that representation from the beginning. It doesn't have to wait all the way until the end, right? And we can see evidence in practice for this happening with this graph. So the y-axis is the mean attention distance. So this is essentially the distance between the original query and the key that it ends up using. So the attention distance between here and here would be 1. Attention distance would be like 2. Attention here would be like probably the max, right? And then you essentially average them and you weigh them by like how much they actually use it, right? So if the dot product between this and distance high, then this distance ends up weighing high. So if in practice this token ends up really wanting to attend to this token, then your mean attention distance will be really high. If in practice this token like doesn't really care about all the other tokens, just cares about its neighbors, then the mean attention distance is going to be really low. So we see is in the earlier layers, it does in fact use use tokens that are far away from it, right? So we see in practice that the transformer does take advantage of having this global receptive field. So a couple cons for this architecture. Well, one thing is that the patches are not very fine-grained, right? So for something like segmentation, if you want like this fine like boundary, because we segment it into like patches from the beginning, you're not going to have a representation of this, right? So your output representation is also not going to be very fine-grained, and that might present some issues. Another thing is like fine-grained image classification and anything essentially where you need a lot of detail, because the issue with VITs or this particular architecture is that you sort of just glob all the patches together. So you might lose a bit of detail on that front. So yeah, so the takeaway from these two models is sort of this idea of like generality, right? So we want to be moving away from it's the idea of moving away from models that have a lot of inductive biases and towards more general models, right? So any domain-specific biases or domain-specific like features should be learned from the data instead of being hand-engineered, right? We shouldn't have models that are specifically made for images or models specifically made for text. It would be maybe a good idea to have models that are specific to they're models that can be used on anything, and then they're only specialized once you train them on data, right? So I'm sort of like holding it back a bit and saying like maybe this is a good thing, because it's hard to have like hard evidence of which like research direction is the best, but some intuitions on why we might want this include so just like the historical aspect of like where AI is going, I guess. Like if you think of what AI was in like the 60s, right? It was like expert systems, right? It was these huge, essentially like dialogue trees or like if statements where you hand engineer every single possibility, every single user input, and then like if the user inputs hello, then you should also output hello, right? Versus more recently with deep learning and stuff, right? Now that we have access to all this compute and all this data, we can take advantage of more learned algorithms that learn their own features from data, and we see that in the past they worked better. So they work better. So sort of the natural progression to more and more general models, more and more models that learn from data instead of being hand engineered might be a good thing. Yeah. So it also lets us easily combine domains. So if our architecture and like learning scheme is general enough, then we don't have to craft like if we want to build a model that does like image captioning, right? That needs to process both image and text information. So if we have the same model and we're able to pre-train them on both image and text, then that's great. We've like saved the step of having to like engineer an actual model, I guess. Yeah. So an example would be like Gato. It was a model released I think like 1 or 2 years ago by DeepMind where they pre-trained transformers on like text, images, just like Atari games, and they're all modeled with transformers, which is pretty cool. So another reason why you might another like takeaway would be this shift towards more self-supervised and unsupervised learning. So this is learning without labels, right? Learning without label data. So a reason might be like recall earlier, right? Transformers need a lot of data to work, but they work really well if you have it, right? So transformers in particular have like this GPU and TPU compatibility that allows us to scale really easily with the hardware that we have, right? But the issue is that we have a lot of like random data that we can scrape off the internet, but we don't have a lot of like label data or quality label data, I guess, right? So self-supervised and unsupervised objectives that don't use labels would help us take advantage of all this like random data online and sort of save us the trouble of having to annotate everything, which, yeah. So yeah, transformers give us generality and where biases are learned from data instead of handcrafted. And the idea is we let everything attend to everything. And if we give it enough data, it should know what to attend to. And hopefully it'll do it better than we could sort of hand engineer. So I'll go pretty quick for these last couple of these. These are just some specific examples of how maybe VITs are used in practice. So maybe this is a paper that's sort of moving towards what I talked about in the previous 2 slides, which is emerging properties in self-supervised vision transformers. So it uses an architecture that's similar to an image is worth 16 by 16 words. So it does the patch stuff. And it also does a self-supervised objective similar to image DBG. So that's the first example. So it's able to take advantage of all of this random like image data that doesn't have labels and is also efficient because it uses the patches, right? So what we found is it produces really good image representations. It sort of does it in a similar way to before with like the linear layer, but instead of a linear layer, it uses the k nearest neighbors. Don't worry about it too much. But essentially, it produces good enough representations such that like a really weak classifier can then use those representations really easily to do image classification at high accuracy, right? Another advantage is that representations produced by this model can retain sort of scene layout information and object boundary information. And so it might be able to be used for stuff like video segmentation. So see that here. So this shows the self-attention on the CLS token on the last layer. So the self-attention weights sort of showing what the CLS token finds interesting with respect to the rest of the image, right? So we can see that even though it wasn't trained on any images, even though it wasn't trained on any labels, it still is able to figure out like what the interesting parts of an image are, right? So it's able to figure out like the bird or like the boat and ignore the background without any like explicit supervision of you need to classify birds or you need to classify boats. Just by training on random images and with this architecture, it's able to sort of figure out these boundaries, which is pretty cool. So yeah, so another thing is that VITs are used a lot these days. Like this is the Imagenet Leaderboard. So this is just image classification. Took this sometime during the summer, the screenshot. So the top couple models are all vision transformers. So a couple of things to notice is the parameter count, which is this middle column right here. It's all like 1 billion plus, right? So it shows that we can scale transformers really well. We can scale them really easily. Another thing to notice is on the right side, you have this like JFT 3 billion data set. It's this huge like pre-training data set with like 3 billion images. I don't think it's unsupervised, but it has sort of the weakly the noisy labels that we talked about earlier, where like your labels are kind of bad, but if you have enough images, then they sort of like cancel each other out, I guess. or like it's more like there's still enough signal that your model is like able to take advantage of this huge data set. Yeah. So you need a lot of parameters, you need a lot of data, and then you perform really well. So how you actually get to this point, like how do you get from the first architectures we talked about in the beginning to this like top one on the leaderboard. So one example is just to make them larger and train longer. So it takes the same architecture as an image is worth 16 by 16 words. That's the patch stuff. And then it essentially they do a bunch of tests with different levels of training time, different architecture sizes, different amounts of data used to train. And then they graph them and they try to see insights. They try to garner insights into how to scale these models and if they scale after a while. So what they found is that better representation scales with compute time, model size, and data set size. So if you scale those things at the same time, then you perform better, which is maybe a bit of a obvious result. But another thing is like large models are also more sample efficient, so they need less training samples in order to get the same performance, right? So you need to train them on less samples in order to get to the same performance. So that's another thing that you also see in text as well, like language models. They also have some engineering stuff just to improve training performance and fine-tuning accuracy. And their 2 billion parameter model ended up getting the state-of-the-art on Imagenet at the time. I think they don't have that anymore. Let's see. So yeah, so some graphs from the paper, essentially just saying what we had earlier, which was the blue means like the more blue it is, then the smaller models, the smaller the model you have, the smaller the circle, the smaller the data set you have. So sort of on, and then the x-axis is like training time, right? So on the top, or more like top left, if you have a really small data, or it's really small model, it doesn't really matter how much data you give it. At a certain point, it sort of levels off, right? So that's the model size bottleneck. And then on the bottom right, if you have a large enough model, but not enough data, so this like tiny thing right here, so you have a pretty large model, but a pretty small data set, then it tends to level off as well. So yeah, if you scale up the three factors at the same time, data, model size, and compute at the same time, then you perform better, which is pretty cool. Yeah, so as the last thing is like vision transformers and CNNs. So this is like sort of a hybrid architecture between those two. So recall that the lack of inductive biases is bad if there's not enough data, right? So it's often that you want to train a model, but you don't have access to this like 3 billion size data set, right? So solution would be to add some inductive biases into vision transformers. So two issues with transformers is that one, they're missing translational equivariance. So that's sort of the bad thing I talked about earlier. But turns out like it's actually good if you don't have enough data, right? It's still a beneficial thing if you don't have all this compute time for the transformer to learn these good feature representations by itself. So how do we add this back into the transformers? Well, one way is to add a weight value when you're calculating your attention weights. So and this weight value is only dependent on the relative position. So we have this feature or this token, right? And this gets projected to key query value. And then we have maybe this token key query value. This is token in the middle. It also gets projected to key query value, right? So we have our query value comes to this key, query value comes to this key. And then we essentially, the way like it tends to these tokens is by doing just a dot product between this key representation and this, or this query representation and this key representation, right? So we essentially just add on this learned weight value that's dependent on the distance from here to here. And that's also dependent from the distance from here to here. So for example, if you want to encode sort of this idea that let's say you want tokens that are closer together to be weighed more, right? You think that tokens that are closer together will naturally be more relevant or something. So in that case, if you were to have just a vanilla transformer learn that, it would have to sort of alter the representation for each of these key query values, right? It also have to probably alter it for the positional embeddings as well. So it'd have to do that for every single one of these tokens. Whereas if you have this learned weight value, right, this learned set of like weight vectors, then you can just say like W0 equals to 0, W1 or W0, if the distance between two tokens are 0, then you should add this like huge weight, right? If the distance between two tokens are small, then you should have like a negative weight or something, right? So a lot you sort of find with images, there's a lot of features that are that don't depend on their absolute positioning and only depend on their relative positioning. And this extra weight vector, this extra learned parameter, lets you encode that really easily in like a really efficient way instead of having to learn it for all of your tokens. So yeah, another thing that you need to change is the quadratic time with respect to spatial size. So remember before that if your input sequence is 256, because the transformer is O of n squared, that's kind of not great sometimes. So one way you can sort of fix this is by pooling, like doing max pooling or something, after the output of each block. And another sort of thing you can add is just to add like convolutional blocks in with transformer blocks. So just combine them. Yeah, so I think it would probably make more sense with the full architecture. So for the beginning couple, you have convolutional blocks because remember vision transformers, they don't handle long sequences well. So you want the convolutional layers to handle the long sequences, and then after it's downscaled by a couple times, then you can use your vision transformer, and then it might be fast. And then also notice the sort of dimension of each of these blocks. So I think this is the input dimension, and the input dimension to each block is downsampled. So you pool before each input, which makes it a bit faster. Yeah, so to conclude, vision transformers and their associated like self-supervised and like unsupervised training schemes are sort of the next step in more and more general models. And general meaning like less inductive biases and less hand labeled stuff, right? And sort of transitioning from hand engineered features to maybe like vision transformers later on. And also they also require a lot of data as transformers tend to do. Also like VITs are really scalable because transformers work well with like our compute hardware, and so they perform really well, right? We can scale them really easily with our hardware, and we can also we can scale them during training time really easily. I think that's it. Yep. Does anyone have any questions? Yes.
For the coordinate data, is that a self-supervised training method?
I think it's supervised. Yeah. Yeah, because I guess the idea would be that you don't have a lot of data, and that tends to curve. Yeah. Yeah. So if you have any questions, feel free to ask on that STEM. I'll probably check that and yeah, answer any questions and stuff. So.